Okay, so we're starting. Okay, in today's video, I'd like to go over the magnetic field near a long, straight, current-carrying wire. But before I do that, I just want to let you know it's a Friday morning. I've had a liter of Diet Mountain Dew. I was watching CBS this morning, and I saw a poet laureate, Amanda Gorman, and it was very nice what she said, but I couldn't understand how that was poetry. The poetry I know is something more like this. Roses are red, violets are blue. If you think you're going to pass this course, then you are truly screwed. So, here's what we're going to do. I'm going to use this blue marker here to represent my wire. And right now, the wire is pointing vertically up. And this end of the wire is going to indicate which way the conventional current is flowing. So in this case, the conventional current, which is just part positive charges, is moving straight up like this. Okay. And what we're interested in is, hey, what's the direction of the magnetic field? But before I do that, I wanted to point out this formula. So this is the formula we're going to use for a straight wire. Here's our magnetic field, which will actually be a vector, and it will be in the unit Teslas. Here's a constant that you can look up in your notes. Here's our conventional current. Here's 2 pi, and d is just simply the perpendicular distance you are from your wire. So it could be 20 centimeters, which would be 0.20 meters. Now, the key thing about this formula here, this is pretty much a plug and chug, so that's not the problem. The problem is when you do this formula, since B is a vector quantity, how will you indicate the direction? And that's what I want to concentrate on today. So this is what we're going to do. Since we're talking about conventional current, that is a flow of positive charges. Well, anytime we have positive charges, we will always use our right hand. And one of the things they tell you in the notes is using your right hand, the thumb indicates the direction of the current, and your fingers will curl around the wire, and that will indicate the direction of the magnetic field. By the way, if we were actually dealing with real current, that is the flow of electrons, you could use your left hand, and the deal is negative charges go in the opposite direction. You still get the same effect in terms of magnetic field direction. So here's what I'm going to show you. My thumb will be lined up with this right here. Now, if I line up my thumb and I look at my fingers, they're going into the board. Therefore, the magnetic field on this side would be like this. So remember our little symbol for indicating when a vector is going into the board? Okay, the feathers of an arrow you're looking at. But this is the other thing. If you take your thumb and now you go on this side, notice that your fingers would have to come out of the board. And once again, go over here, and you'd have something like that. If we should change the direction of this, of course, what would happen is, once again, taking your thumb, if it's going in on this side, then it has to be coming out on this side. So when you plug in your numbers, all the data, whatever you have here, you get a number for this, the magnitude. If it's coming out on this side, you would indicate the direction with a circle and a dot in it. But there's one other thing I wanted to show you. Let me go back to this, and that is the following. So far, we've been dealing with the side view of a wire. What we're going to do is we're going to pretend that if you took this wire and you always tip it so that the top is coming up. So whatever the top is, in this case, if the current was flowing this way, this is the top. On the other situation, when the current was flowing down, this would be the top. So we're going to look at the top view. And one of the reasons why we want to look at the top view is, now let me show you this way. If my thumb is curled around here, you can see how my fingers are circulating around like this. It turns out that that circulation would correspond to a counterclockwise rotation. So my magnetic field is going around like this. But what does that actually mean to say the magnetic field is going around like this? Well, I made these little wooden magnets, okay, and here's the following. The B vector here, it's understood that you can draw it as an arrow. The arrow is always coming out of the north end and is always going into the south end of a magnet. So in this case, this would be the head of the magnet this way, north this way. Over here, it'd be like this. So when you go like this, think of my fingers as being the North Pole. Going around, you get like this. And finally, you get it like this. So that's the way we represent it with a magnet. One other thing to note, if I wanted to indicate the direction of the current, well, since the current, you might remember, was coming out, I could do it like this. So I could say, okay, so here is a counterclockwise rotation for the magnetic field vector. The current is coming out. That's what that represents. And so my thumb, once again lined up, you can see how my fingers curl this way. Now, let's go ahead and reverse this. Now, unfortunately, to reverse this, this is not going to actually stand up, but let me show you this way. If I were to take my thumb, go in the direction, okay, of the current, so I've got like this, my thumb's going down, you can see that my fingers are in a clockwise rotation, then I would have a card like this, okay, and like I said, this is not going to stay up, but now because, okay, I'm going to put this down, but because my magnetic field vector is going this way, it means if I place little bar magnets around this, they would line up like this and such. And in addition, the only way I could get my fingers, which represent the North Pole, to go this way is if the current was actually going into the board. Now, this is the top view. This was the side view. Now, I'm giving you this information because this information is going to be used in another video whereby I show you what will happen when two wires that are parallel to one another and have current flowing through them, how they interact with one another. And that's the end of this video.